Welcome to the second part of the chapter 2, module 2, where we are going to discuss about some properties of the norm of linear function. So first property is that for all a belongs to L Rn to Rm, the norm is from 0 to infinity. So now positivity is well understood, but it will also goes to infinity because of the definitions contains the supremum. Now the second property is that if A belongs to an Rn to Rm, for all x belongs to Rn, then mod of Ax is less than equal norm of x multiplied by mod of x. So let's have proof of this theorem. If x is equal 0 belongs to Rn, then Ax is equal A0 is equal 0 because linear functions take 0 to 0. Now in this case you will have directly this properties holds, so therefore, and norm of x is equal 0, so therefore this implies mod of Ax is equal 0 is equal norm of A mod of x. So to prove that, the other part, that let x is not equal 0. Let 0 not x belongs to Rn. So to do this, we will take that unit vector u is equal x over mod x. Clearly, mod of u is equal 1. Now we are going to define the norm. So we know that norm of A, which is equal supremum of, so let's y belongs to Rn, mod of y is equal 1, and then absolute value of A y. So which is greater than equal absolute value of A u, because u is one particular unit vector, but this is true for all y, okay, whose mod is y is equal 1. But in this case, we have here particular u, we satisfy that condition, so therefore the supremum will be greater than equal this A u. Now this in particular will gives us A u is less than equal norm of A. So now what is u? U is given as x over mod of x. This is less than equal norm of A. So now mod of x is scalar and A is linear. So we can write it as this is equal mod of x, Ax less than equal norm of. So there is absolute value. So we'll take this absolute value. So therefore absolute value of Ax is less than equal this. So this will give you absolute value of Ax is less than equal norm of A, absolute value of x. So this validated the second property of the norm of linear function. Okay. Now I will move to the next properties. The third property says that norm of A equals 0 if and only if A is equal 0. So this is very easy to prove. So we are not going to prove. Now take the fourth property. It says that if A, B both R belongs to Rn to Rm and lambda is any real number, then the scalar multiplication lambda a will be absolute value of lambda norm of a, and norm of a plus b is less than equal norm of a plus norm of b. Now we have our fifth property. It says that if A belongs to Rn to Rm, B Rm to Rm, such that composition is possible, then norm of B composition A is less than equal. Start the proof that for all x belongs to Rn, for all x belongs to Rn, such that mod of x is equal to 1, we have B composition A x, this is equal B of Ax. So B of Ax, and then by the previous property, second property will have this is equal less than equal norm of B, and then mod of Ax. Again apply on this Ax the same property, so we will get it here norm of B, then norm of A, and mod of X. Value of B composition Ax. So now we have norm of B composition A. So this is equal supremum of x belongs to Rn, mod of x is equal to 1, and the absolute value of B composition A x with mod of x is equal to 1. So this is the definition of the norm. So therefore, now if it is supremum of that, and in particular if it is less than equal this, so we'll get it here. This is supremum of mod of x is equal to 1, and then we will have is norm of B, norm of A, mod of x. So mod of x is equal to 1, so therefore this is equal norm of B multiply norm of A. So we got next part is a theorem. It says that if A is from Rn to Rn, then it is a continuous on Rn. Okay, so let A belongs to L, Rn to R, then mod of A. So this is equal mod of A x minus A Okay, in the next theorem, we are going to prove that A from linear Rn to Rn. Be careful on this. This Rn to Rn are continuous on Rn. So let A is belongs to L, Rn to R. Then for all x belongs to Rn, and fixed A belongs to Rn, Ax minus A, which is equal mod of A x minus A. So this is equal norm of A mod of x minus A. So therefore, if x tends to A, then x minus A tends to 0. So therefore, we have here, so this implies mod of ax minus aa tends to 0 as x tends to a. So this implies ax tends to aa when x tends to. So this is the definition of the continuity. So therefore A belongs to L, Rn to Rn is continuous. Okay, now we have some generalizations of the previous theorems or the matrix form of the theorems. If A is from L Rn to Rm and the matrix for A is equal Cjk, then the associated matrix of A is like this, then norm of A will be sum of the each component of the matrix whole square and then square root. So this is basic formula of this one. So it's a absolute value, sum of the absolute value of the all the entries of the matrix. Now next theorem is that if for all x belongs to Rn and norm mod of x can be written as a supremum of u belongs to Rn, norm of u equal 1 and then u dot x. So for any vector u from Rn whose absolute value is 1 can be written as mod of u dot x.